Hi everybody, welcome back to this new video. I'm gonna show you the new enhancements for this rDUINOSCope. The main enhancement that it is in this new version is the ASCOM support. So there is now a new ASCOM driver which will allow to remote control your rDUINOSCope. We're gonna talk about it later. We're gonna talk also about some improvements that are not visible but also very important. So I'm going to show you now a list of the new functionalities. In addition to the latest improvements brought by the latest version, here are the new features. I made a complete code revision and removed the S string class. This class, which manages strings in Arduino, causes memory corruption because it fragments the memory over time. The Arduino DUI has a lot of memory and we might think that would be a problem using this class, but there were actually many variables using this class in the code and there was bugs caused by this phenomenon. We were having particular problems with memory corruption when storing option information on a memory card, so I prefer to remove everything and replace it with shards to avoid potential bugs. Second major modification, the motor management. I used timers, so there is a timer that was already used for the tracking in this code. I used two other hardware timers for the Arduino for array and deck movements, which bring a lot of improvements since it increased the speed of the motors and reduced their noise. With the ASCOM implementation, it was necessary to have hardware management of the motors because it caused motor cutout when the ASCOM communicated through the serial port. Once this migration done, it resolved another bug. This was the freeze during the go-to phase when using the Bluetooth. So the motors are now completely independent. There is no longer a CPU load to run them and the system is now smoother. There are no more interruptions due to the use of the ASCOM, Bluetooth or anything else related to the interface. Like I said before, the speed was increased. So here we have a 30% increase. The speed was already doubled by the previous version, so this rDUINOSCope is now 2.5 faster than the original one. On the bug side, there was several mistakes in the alignment star's name. There was a rounding bug with a 1 minute jump in a declination or a right ascension. There was this bug of corrupted data on the SD card because of the string class. The meridian flip that was working only one time. When the object passed the source meridian, the mount was doing the meridian flip, but if you go back to an object further east, when this object passed the meridian, there were no meridian flipped anymore. The screen brightness option that was not working in the option page, I corrected it. The amount of move when using manual move on Bluetooth or with the joystick now depend where the object is in the sky. Application freeze when using Bluetooth, and the telescope position which did not appear in the Bluetooth application when using GoTo. On the side of the new functionalities there is now a new menu with a search engine that allows you to search an object in the database using its name, and a brand new ASCOM driver in server version that allows you to make several simultaneous connections. For example, you will be able to connect your PhD2, SkyChart, Nina at the same time. This ASCOM driver allows you to perform common operations such as go to an object from your SkyChart. You also have the option to return to the home position, parking the telescope, and set the park position. You can choose the tracking mode, such as sidereal, lunar or solar. You will be able to set rates that gonna be applied to the amount of manual move. You have the peer side which indicates the position of the telescope relative to the tripod. You can make a synchronization with the map. It can read the radix coordinates. The alt-task coordinates are not read in order to avoid having too much information passing through the serial port. They are calculated by the driver so that it can be displayed in the software. We can import GPS coordinates such as latitude, longitude and altitude. We can do manual move and invert axis. We can abort a movement. and there's auto guiding function, so in this case there's no longer any need to use the small box that plugs into the ST4 port. This means that for those who have built an rDUINOSCope but haven't implemented this part with the ST4 port resistors and optocouplers, their rDUINOSCope become compatible with the auto guiding thanks to this driver. This is because it used the USB port and the ASCOM driver. A little bit about this driver works. The ASCOM driver communicates with the Arduino via commands in the form of character strings, which are sent or received through the Arduino's virtual serial port, so via one of the two USB ports. The commands sent by the Arduino and received by the driver will be processed by the latter, and the commands sent by the driver will be processed by the Arduino. That's why, in addition to the complete overhaul of the Arduino code, there are many functions to manage these ASCOM communications. Therefore, in addition to installing the driver, it is necessary to update the Arduino firmware. This update represents a significant increase in Arduino code, with a 43% increase in lines of code. There are functions to monitor the serial port, functions to read incoming serial port data, functions to process commands, and functions to send the telescope coordinate from the Arduino to the driver. It required a lot of additional programming to be able to integrate these ASCOM functionalities on this rDUINOSCope. To give you a better idea of how I set up this driver to remotely control my telescope, I can show you the telescope installation and the various computer components needed to manage everything. You can see on the accessory bracket that I've mounted a mini PC with an Intel N100 processor and 16 GB of DDR4 RAM. It also has a mini Wi-Fi router, the model number of which I've included here. It's quite inexpensive, works very well, and it's used by many amateur astronomers. I fixed it to the bottom using the mounting plate that came with the mini PC. So let's talk a little bit about the mini PC. This mini PC is based on the N100 processor and is fairly inexpensive. It cost me about $80. However, let's be honest, performance-wise it's not the best, but we'll see what I've put in place to be able to use it properly. So as we can see in this benchmark, this processor has really the same performance level as a desktop PC from about 12 years ago, with the same number of core, the same number of threads, and really the same frequency. However, we can see here that the power consumption is really low. It managed to deliver this performance with a consumption of 6 watts, and it has an integrated graphic processor. If you want to opt for this solution, I strongly encourage you to check out this GitHub page for Tiny11. It's a lightweight version of Windows, so you can see here that in the Tiny11 Maker version all these parts have been removed, and the Core Maker version other parts have been removed as well. I use this one, which also has Windows Defender disabled and Windows Update that won't launch. It's a bit annoying when you are in an Astro session to have Windows Defender running scans or Windows Update starting up, so there are no more problems of slowdowns with this version of Tiny11 Core Maker. So I deactivate these services to gain even more performance. So for installing Tiny11 on a mini PC, it's not a problem. Simply download the ISO from the Microsoft website. Download the ISO that correspond to the system on your PC and then follow the instruction on the GitHub page. You'll need to run a script to compress the ISO, resulting in a lightweight ISO with a completely debloated and optimized Windows 11. Then simply create a bootable disk. There are plenty of tutorials online for installing this version of Windows on the mini PC. You'll end up with a lightweight version of Windows that recognizes the hardware. No activation is required. You get an activated version directly, provided if you've selected the version that installed in your mini PC. So I'm going to put the accessory bracket with the mini PC and the Wi-Fi router on this threaded rod. It will be fixed from below. Next, this is my 3D printed mount for attaching the rDUINOSCope to the accessory bracket. Next, I'll connect the motor cable for declination and right ascension. In the meantime, I've installed the counterweight and will work on the tube. So on the tube, I've all the connectors already attached to an SVBony SV241 box. Here I have a sleeve with a USB cable that will be connected to a mini PC, and a power output for the rDUINOSCope and the mini PC. Here I have a USB cable for the rDUINOSCope, 2 USB cables for the cameras and a power cable for the imaging camera, which come to the end of the tube. Here are the 3 connectors for both cameras. So here is the SVBony case, below are the power outputs, above are the USB outputs, and on the left side are the power and USB inputs. So here's the tube mounted on a mount. Here are the cables that will allow us to connect the cameras that go to the SVBony box. From the SVBony box we have this sheath and the cable for the rDUINOSCope. So let's see where to connect all of this. So coming out of the white sheath we have the USB cable which is connected to the SVBony, and the power return which will power the mini PC. So I'm gonna connect the mini PC power supply and the USB cable to connect the mini PC to the SVBony case. So here we have the power input which will connect last. It goes to the SVBony box and then back to the mini PC and the other accessories. Here we have the connection for the rDUINOSCope, which comes from the SVBony box and will be plugged into the rDUINOSCope. As I showed earlier on the SVBony box, I have a USB cable that I haven't inserted into the white sheath so that I can connect it to the rDUINOSCope like this and be able to pick up the box, step back and not be hindered by 2 short cables. So regarding the imaging and auto-guiding camera, here's what I use. I have an EOS to M48 adapter ring here, onto which I'll mount my OAG. So here the OAG mounted on this EOS ring. This gives me the option of also using a Canon EOS. This is the auto-guiding camera, a homemade Cam10. The Allen key for mounting everything, and this white piece here, it's a spacer which focuses the distance marked on one side when I'm using the Cam87 and on the other side when I'm using the Canon EOS. So there are no more focusing problem. You focus on the main camera and the auto-guiding camera is automatically in focus. So this is the Cam87 homemade, and here is the whole thing with the OAG. And finally I use my little shim to adjust the distance of the auto-guiding cam. So here is the assembly mounted on the eyepiece holder. All that remains is to connect the cables. Here we have the USB cable from the Cam87, the 12 power cable for the Cam87 and the USB cable for the Cam10. Regarding what I've explaining earlier, I used a small extension cable for the power supply of the rDUINOSCope here. You can also use a slightly longer cable and the cable that not go through the white sheath for the USB, so that you can simply take the rDUINOSCope and be able to step back, stand next to it at a distance without being bothered. Now all that left is to plug in the power supply. I'm using this one. I'll give you the model number. It's the largest 12-volt power supply available. I had some minor issue with my previous power supply between the Peltier element, which drove a fair amount of current from the Cam87 and the mini PC. I was experiencing voltage drops. This one is rated at 20 amperes and some user claims that it can deliver 30 amperes. According to feedback, it doesn't overheat even at 20 amperes. So once plugging the rDUINOSCope startup, the camera startup, I'm using the web server I created for this camera, so on my mobile phone. I'm showing it on the computer so I can film it, which allows you to control the camera remotely via Wi-Fi, allows to adjust and set the temperature, turn off and on the cooling system, view a chart to see the cooling stability and so on. Next I'm going to show you the remote control, so I'll turn on the mini PC. I connect to the Wi-Fi network from the small TP-Link router, and then I use RDP to be able to connect to the mini PC. RDP is an application that comes with Windows. You can use the Windows app to connect with a tablet or a phone. And there you go. Instantly I have the desktop. Tiny11 helps a lot for the smoothness of it all. I strongly recommend installing this version of Windows if you don't want any trouble. So I opened Sky Maps and I'm connecting the ASCOM driver. And we're gonna see the screen on the rDUINOSCope that changed. It displays a small green ASCOM remote message, and on the PC we get confirmation that we are connected. So here I have the position of the telescope on the celestial North Pole. I can pick a star on the map, go to telescope, go to this star, and the telescope is going. And there the telescope on the star, and it automatically start tracking. So we can see we have a smooth return flow on the sky chart screen from the telescope position. There is no sudden jerk on the motor thanks to programming via hardware timers. I'm going to show you how to handle simultaneous connections. Here we have a sky chart with the driver connected. I'm going to open another program, for example PhD2. And I'm going to connect the driver so I can use PhD2 for auto guiding at the same time as the sky chart. So I can have the telescope position on the sky chart, use GoTo and so on, at the same time with PhD2. So here we are in PhD2. I click on Connect All, and this is the driver for the Cam10, and we are connected. So there you go, it works with other softwares. It also works with Nina. The driver is compatible with 32 and 64 bits. So here I have the telescope in real life outdoor setting, and inside I have the PC so I can control it to have the telescope position displayed on the sky map. Here we have the scope on the M42 Nebula, and we have the feedback on the KM87. So here I have Aldebaran on my KM87 camera. The auto guiding is active, the driver auto guiding function. Here we have the sky map on another target, and we can see outside what's going on. So that's the end of this video. I hope you liked it. I hope the rDUINOSCope will meet all your needs thanks to this new driver. It's true that this is exactly what was missing compared to competing solutions. So now we have a complete solution that can be used in standalone mode or remotely via ASCOM.